This video goes over how to integrate and differentiate curves that are generated by 2D data. Let's get started. For this example, I'm going to use an actual function starting from 0 to 3. And here's what the function looks like. We can calculate the area under the curve, f area, colon equals, we'll take an integral from x underscore underscore 0 tab x underscore underscore f tab f of x tab x, and it turns out it's this amount. From here, we're going to sample data points from the actual curve and then calculate the area under the curve and compare it with our actual area. I'm going to choose 17 points. I'm going to call the x points a list, which is a sequence of the values x going from the minimum to the maximum, and the number of elements in it is going to be n. The y points can be calculated by applying the function on each of the x points. That means using the tilde, say, to apply to each of these of the x points. So these are the points that we're going to use to do the integration. The first approach will be using a trapezoid rule. This is the default way of calculating the area under the curve. We're going to literally draw lines between each of the data points and then essentially find the area under each of the trapezoid made by each of these lines. You sum up the areas under all the trapezoids, and that's your total area. How do we calculate the area under these trapezoids? We use the signal processing package, signal processing, :dash, we use integrate data. Looks fantastic. And then we pass it the data, x points, y points, and it returns a value. Notice it's 0.456 compared to the actual value, which is about 0.47. The relative error between the trapezoid area calculation and the actual area is -2%. It underestimates by 2%. The next way we're going to do it is using the Simpson rule. The Simpson rule idea is that you take 3 successive points and you build a polynomial between it. So there is a second order polynomial between those 3, then a second order polynomial between those 3, etc., etc. How do we calculate the area under the curve given this particular plot? Again, we'll use the signal processing package, and within it, the procedure integrate data. We will also give it the x and y points, but we will tell it that the method it should use is Simpson. Notice you get a return of 15 significant points. If you have this type of curve, we could have actually calculated the area exactly, f Simpson area, :equals, and again, we could integrate from the minimum value to the maximum value of the function f Simpson, and it returns exactly the same value, but in here to 10 significant digits. The error between the Simpson area calculation and the actual area is around 1%. It overestimates by 1%. The third technique I'm going to use is a spline-fit. A spline-fit applies the same sort of philosophy as using the Simpson rule, but instead of a second order polynomial, it uses a third or even higher order polynomial. So let's make our spline-fit :equals, and this is using the curve fitting package :dash spline open parentheses, and again give it the x points, comma the y points, and make this fit a function of x. Now this is this huge thing, and you can see what it looks like here. In fact, I'll make much smaller, and it varies depending upon what the value of x, and it matches again, as you can see, by a fourth order polynomial. From here, let's make a spline function, make function of our spline fit as a function of x. I will not display it because it's large. We'll make a spline plot which is a plot of our f-spline-fit of x, going from x equals minimum dot dot to the maximum. And again, we will make the y components minus 1 dot dot 1. And now we will display it, plot colon dash display, open parentheses, our D plot, our spline plot, and again, make a size quite large, say 600 by 300. And so you can see it does a better job, a more natural way of filling in the data. We can now actually calculate the area, spline area, because we just simply have a function. We integrate it from the minimum to the maximum of our f-spline function of x, and we get a value that looks like this. When you ask what is the error, it turns out this error is even smaller. It's on the order of about 0.4%. Differentiation. Differentiating a curve made from data points is fraught with problems, but the basic idea is we're looking at the difference in the vertical direction divided by the difference in the horizontal direction. If we fill out these points and we plot them, we can get a curve that looks like this. But instead of going through this technique of creating this sampling sequence, we have the spline fit. And with the spline fit, we can actually create our own spline fit function. So f spline prime is the derivative with respect to x of f spline of x. Again, I'm not going to display it because it's huge, because it varies depending upon what the x value is. But I'm going to plot it, and as you can see, like the gray bars, this is the derivative of the spline fit, and it actually is a much smoother and matches better the derivative using just a straight slope technique. In the document associated with this video, I go over the different types of formats that Maple can handle: lists, vectors, and matrices. As always, if you have a question, leave it in the comments and I will respond fairly quickly. And finally, if you want to see the whole series, go to the YouTube channel at Mapleprof or go to my website, gould.prof/learning-maple.